Well, we're going to have a look at the scalar or dot product in this session, and it's all about vectors, and it's a great and very interesting little topic, so let's get straight into it without any further ado. What is the scalar or dot product? Well, actually it's a very interesting concept, but it does not result in a vector. It is the product of two vectors, but which results in a scalar result, or just a number. So it is the product of two vectors, as I said, but it produces a scalar result. A scalar result, not a vector, okay? That's the most important thing about it. Now, you're probably wondering, what do we work this thing out for? Well, it'll become clear in a later session while we use them. It's all about what are called vector resolutes, and they use this scalar or dot product, okay? So A dot B is the notation used for the dot product, that is, the dot product. Remember the dot, please. Don't forget the dot, and do a big, nice, big, clear dot so it's clear what you're doing, okay? Definition: A dot B, where A and B are two vectors, is equal to the magnitude of A times the magnitude of B times cos of theta, where theta is the angle between them. Alright? Now, yes, A dot B, that's what that says, and that says the magnitude of A, that says the magnitude of B, and that says the cos of the angle between A and B. Alright? So far, so good, alright? Very good. Now, NB, nota bene, which is Latin for note well, and what you've got to understand is, what do we mean by the angle between the two vectors A and B? What we mean is the tail-to-tail angle, so that you've got to have the tail of A joined up to the tail of B, and then theta is the angle between those two tails joined up. I'll show you. See that? That's what I'm talking about. So therefore, what am I saying? This is vector A, and there's its tail, and that's joined to the tail of vector B. So that angle in there is the angle between them. Don't ever get that confused. If you have a nose joined up to a tail, and that does also form two lines, which you can form an angle from, that's not right. That's not the angle theta. It's actually it works out to be the supplement of the angle of theta, which is wrong, okay? So please get that right. It's tail to tail. The tail angles, tail-to-tail angles will never exceed 180 degrees or pi radians. And if you think about that, that makes perfect sense. If you were to draw a couple of lines and try and make the angle between them, and try and make that angle progressively bigger to go beyond 180 degrees, well, then you'll see that just looking around the other way, you'll get the actual angle theta, which will still be less than 180. If you just play with it, you'll see what I'm talking about. For example, I'm just going to do a little diagram for you here. Yeah, okay, there's U and V. Now, where's the angle between them? You have a look. Where do you think the angle between them is? Where do you think? Come on, lock something in. Yes, that's it, right? That's it. Now, if you were to imagine, if I just try and just get you to conceptualize this for a minute, well, wait a minute, I'll get that around the other way. There, now, if I was to drag that vector V backwards, so that the head of it was there, okay, so I'd then be going, right, tail to head to tail, right, then this angle in here would be the angle formed by that, which would not be the angle between those two vectors, because that would be a head to tail situation. Do you get what I'm trying to say? You must have tail to tail joined to get the angle theta, and be very careful with that. Please be careful with that. It's really important. Okay, so here's an example. If the magnitude of vector A, that means, did you know that means the magnitude? That thing there means the magnitude of vector A is 5, and the magnitude of vector B is 4, and the angle between them is 45 degrees. Find A dot B for you and me. Okay, well, that's pretty straightforward. So A dot B is magnitude of A times magnitude of B times cos of theta, and we're given all the information, aren't we? Yeah, well, that's going to be 5 times 4 times cos of 45, which is 1 over root 2, which gets us 20 over root 2. And you can leave it like that. We don't care about rationalising surd denominators. It doesn't matter. So don't get all hung up about it and try and print it up and make a mistake, in which case you'll lose marks. That's fine like that, okay? Alright, goody. What's next? The properties of the dot product. Yeah, that's pretty important. We better cover that. There are a few of them. So we know that A dot B is equal to B dot A, because the order doesn't really matter, because you can see that the magnitude of A times the magnitude of B times cos theta equals the magnitude of B times the magnitude of A times cos theta. It doesn't make any difference. So that's correct, isn't it? Next one, if you multiply by a scalar, it makes no difference at all, okay? And that's kind of intuitive, isn't it, really? I mean, K times A dot B is really the same as KA times dot B, and it's also the same as A times A dotted with K times B. They're all the same thing. Yes? It makes sense, doesn't it? Good. Next one is, this is a very obvious. This is that A, vector A dotted with 0, it comes to 0. Well, of course it does, because magnitude of A times magnitude of 0 is 0. You don't even need to worry about the cos theta, because there isn't any anyway, because you can't form an angle if you don't have a length of a vector. So that's pretty obvious, yes? You agree? Good. Now, what's this one? Now, this is actually a very handy one. This dot products work just like algebra. You actually can prove this, but I haven't got time to prove it in this session, but just believe me, will you? A dotted with the result of B plus C is equal to A dotted with B plus A dotted with C. It just works out. So it's nice and handy. It just works like normal algebra, okay? It's sort of dot product algebra. Now, what's this one down here? If A dot B equals 0, well, what does that mean? It means, this is what it means. It means that either the magnitude of A is 0, or the magnitude of B is 0, or cos of the angle between them is 0. Now, if A and B were both non-zero vectors, then you'd only be left with the possibility that cos of theta equals 0, and if cos of theta equals 0, the cos of what angle equals 0, ladies and gentlemen? Yes, 90 degrees, which means, to all intents and purposes, if you've got two non-zero vectors, in terms of their lengths, if you dot them and you get 0, it means that they are perpendicular. Now that's really, really that's pay dirt, that one. That's used all the time in vectors. So can you please lock that one away so you can sock it to them when the time comes, yes? Good, there's two more. If A is parallel to B, then A dot B is just going to be magnitude of A times magnitude of B times cos of 0, because that's going to be the angle between them if they're parallel, right, pointing in the same direction, and cos of 0 happens to be 1, so it's just magnitude of A times magnitude of B. Get it? Good. That's, how many have we done so far? 1, 2, 3, 4, 5, 6. Goodness, we're doing a lot of these. Yes, because cos of theta is cos of 0 equals 1. There's one more. Here we go. A dot A. Now, look, this is really important too for vector proofs, which are coming up in a couple of sessions. A dotted with A is the magnitude of A times the magnitude of A times cos of 0. Cos of 0 is 1, so A dotted with A is magnitude of A squared. Right, now, these are really all important, but the ones that you tend to use, this one here tends to come up in vector proofs. This one tends to come up in vector proofs, maybe, and this one here, you just use that all the time. All the time. So, you know, that's really probably the Emmy Award winner for these little properties of dot products. All right, over the screen we go. Good. Oh yes, same thing, because cos theta equals cos of 0, which equals 1. Yes, good. Now we're over the screen. Now this is very amazing. This one. This is a dot product, but in IJK form. Okay, we've just done the dot product in its basic definitional form, which was A dot B equals magnitude of A times magnitude of B times cos theta. We'll have a look at this. This is just a mind boggle, this one. You ready? Let A, vector A equals A sub x, that's A, the amount of A in the x direction times I, plus AY times J plus AZ times K. Do you know what I'm talking about? That's the component of A in the x direction times I, which is a unit vector in the x direction, plus the component of A in the y direction times vector j, which is a unit vector in the j direction, plus the component of a in the z direction, times k, which is a unit vector in the z direction, right? Get it? Alright, now same deal for b, same thing analogously. Now we're going to dot a and b, and you need to fasten your seatbelts because we're going to blast off. And how? Ready? Right. Oh, here we go. So A dotted with B equals this beast dotted with this beast to create super beast. Yes, it'll be a feast of beast. Now, you ready? I told you. Now, actually, it comes to a beautiful result, right? We're going to have to multiply all those things out, okay? Here we go. Right, the first one, that's ax bx I dot I. Ready? Here comes the next one. Plus ax by I dot j. You getting this? Yes, I know. It's a mind boggler, isn't it? Next one is ax bz I dot k. Okay, now here comes the next three. Plus ay bx j dot I plus ay by j dot j plus ay bz j dot k. Yes, are you hanging in there? Three more to go. Plus az bx k dot I plus az by k dot j plus azbzk.k. My goodness. Right, now we're finished. Now, you watch this. You ready? Pick yourself off the floor. There's an incredible result here. It comes out of all this, right? Watch. Now look, there's our a three-dimensional, or my attempt at a three-dimensional diagram, where I've got the x there, x-axis, and the y-axis perpendicular in a horizontal plane, and then we've got the z-axis sticking up and down, right, vertically. Now, here's my I, which is a unit vector in the x direction. Here's my j, which is a unit vector in the y direction, and here's my k, which is a unit vector in the z direction. Now, ladies and gentlemen, I want you to cast your beady eyes on all of that catastrophe, because of those 9 terms, 6 of them are going to vanish. Did I make that dramatic enough for you? Well, which ones are going to vanish? Now you think about what I said in that previous screen about the properties of vectors. If two vectors were perpendicular, what did I say that cos of 90 degrees equaled? 0, didn't I? Well, you have a look. You've got lots of perpendicular vectors there. Yes? You watch this. But I dot j equals j dot I equals j dot k equals k dot j equals I dot k equals k dot I. And they all equal the magnitude of the first one, which is they're all unit vectors, times the magnitude of the second one times cos of 90, because they are all perpendicular. You see, aren't they? And what does that equal? My dear friends, it equals 0. Good grief, you're saying. I know. Wonders never cease. So, watch this. Oh, what have I got written there? Yes, of course, and to finish off the story, I dot I equals j dot j equals k dot k, and that equals, because they're all, parallel to each other, because obviously, they are parallel because they're the same thing as each other. Therefore, that equals 1, which is magnitude of, they're all magnitude 1. 1 times cos of 0. And what's cos of 0? It equals 1. So come on now, have a look north and you'll see all the crossing out extravaganza. Ready? There it goes. Look. Pretty amazing, eh? Now I told you had a good result. Now here comes the knockout punch. So A dot B in IJK format is just the coefficients of the x terms of A and B multiplied together plus the corresponding the coefficients of the j terms multiplied together plus the coefficients of the k terms multiplied together, and that, ladies and gentlemen, is your answer, and that deserves a mega box because that's supremely, El Supremo important. You have to know that. Oh yes, you do. You have to know that. That's core knowledge, right? So we've now got two definitions of dot product. We've got the fundamental one, magnitude of A times magnitude of B times cos of the angle between them, theta, and we've got this one for dot product form. Okay, now we're going to do, I think we're going to do an example, yes. Right, what have I got here? If A equals 2i minus root 3j plus k, and B is minus 2i plus 1 over root 3j minus 2k, find A dot B. Now, they're in IJK format, guys, so we're just going to simply do what I just did, what I proved on the previous page, and we're going to do that, right? That's the, what's that? That's AX, that's BX, if you like. That's A sub Y, that's B sub Y, and that's A sub Z, and that's B sub Z. You just multiply them together, right? And you get your answer. It's as simple as that. So let's get the next line. There it is. Goodness gracious me. How marvellous. So it looks like it's minus 7, and we're in heaven. Yeah, that's it. That's the dot product for you, okay? Pretty simple, eh? Yeah. Congratulations to all of us for getting that right. So it's beautiful, isn't it? Now, here comes the next thing. This is a very, very important bit which relies on those two previous results of how to get the dot product. Now, you better watch this carefully. This is where they really start to hit you with the questions where you've got to really have a good understanding here. Now, okay, so to do this, guys, to find the angle between two vectors, we combine both formulae, as I said, for dot product, the definitions in basic form and in IJK form. We combine them, and we then solve it for cos theta to get the expression for cos theta, and here it comes. So we can say that if A dot B is equal to magnitude of A times magnitude of B times cos theta, but it also equals that stuff from the dot product form, then solving for cos theta, what do we get? Yes, we do. Whoopee-doo. There it is, guys, in all in glorious technicolor. That's what you need. That's what you need to solve for the angle between two vectors, right? There it is. And it's really easy to do, really easy to do. But there's a few booby traps along the way, so I'm going to show you how we might do that. Now, I think this is, this is my example, okay? You've got to watch this carefully. So capital A, capital B, capital C are points defined by position vectors, little a vector, little b vector, and little c vector, respectively. So there's my vectors, little a, little b, and little c, in terms of I, j, and k, right? So what are they asking us to do? We have to find the angle ABC. Okay, ABC, correct to the nearest degree. Now, look, ladies and gentlemen, please, my mantra for anything in maths, particularly in vectors, is draw a what? Yes. Starts with D and ends in diagram. Draw a diagram. Now, it doesn't have to be accurate. In fact, it'll be very difficult to make it accurate. But just a schematic will do, like this. Just a schematic. All I care about is having something visual, and you'll see why in a minute. Look, so I've written there my disclaimer. This is a schematic. It's not the actual points, so don't start complaining about them not looking right. I'll fill in the details now. Okay. In fact, they're three-dimensional vectors. I'm only showing x and y, but it doesn't matter. It's just a schematic. So there's the origin there, down there. Got it? Yeah, there's your origin, and this is point A. This is point B, and this is point C. Now, these make up position vectors because we're relative to the origin, which is at 0, with your I and your J and your K. So, okay, I'm putting the coordinate points in. There are the coordinate points, which you can see correspond to these vectors, right? So A is 1, minus 3, and 1. So that corresponds to I minus 3J plus 1K. Get it? Right, that's the deal. Now, having done that, my schematic diagram, I've got to work out angle ABC. So B is the middle pronumeral, so that's going to be the vertex of the angle I have to find, right? So let's draw this stuff in. Yeah, so for angle ABC, we can use, we can use vectors B to A and B to C. Now, you have a look at this. This is really important for you to get this, guys. Yeah, because basically, I'm using B going out to A and B going out to C because they emanate out from B, so that they form tail-to-tail angles at B, right? That's what I want to do. I want to get the angle between those vectors, so they want to be tail to tail. That's so important, okay? So don't go doing vector AB and vector CB. You go out from where the tails are, right? Then you've got tail to tail vectors, haven't you? Yes, you do. You think about that. I'll draw it in for you. Look. See? That's what I want. I want that angle in there, which I've showed you. See? So if you want that angle there, you want tail-to-tail vectors, and that's how you do. You make that the tail. So that goes from there, tail to head, and this goes here, tail to head. Are you with me? Good show. Yeah, you're getting it. So, alright, so now I'm going to work out what the vectors are. Now, the quick way, the quick and dirty wolfy way, is when I'm going from B to A. Well, look, the rigorous way is to say, ooh, well, that is BO plus OA, yeah? And then to do that, you would go minus OB, which is BO, minus OB plus OA. But look, I just do the quick and dirty way. I do it this way, guys. I say, well, this let's have a look at the x-coordinates. That's minus 1. This is plus 1. So what have you got to do to get from minus 1 to plus 1? Well, you've got to go up 2, don't you? So that's 2i. See? See how easy it is? That's how I do them. So BA, that's how I worked out BA. Now, with BC, you think about it. What's the x-coordinate of the x coefficient of the I term for B to C? Well, we're going from minus 1. That's the position, the x position at B. Then we're going down to C, which is plus 2. So we're going up 3, aren't we? Yeah, see, you get how to do it? It's so easy, isn't it? Now look, we're nearly there, guys. We're nearly there. We've got BA and BC for you and me. And look, we've just got to go through the motions now and use that formula. I'll have to get the magnitude of these, the magnitude of each of them, because that's in our formula. Yeah, so you just cruise along with me and we'll see how we get this stuff so easily. So magnitude of BA is Pythagoras in 3 dimensions, which we covered in a previous presentation, didn't we? An introduction to vectors we did. That looks like 3 to me. Goody. Now, what about the next one? B to C. What's the magnitude of that B going to be? Well, you think about that. It's going to be the square root of 3 squared plus nothing plus 2 squared. Looks like 9 and 4 is 13. Root 13, I'd say. What do you think? Am I right? Yes, I am right. So that's fantastic. Well, look, we're all set to go now. All guns blazing. Let's go for the knockout punch. So we're saying that... I hadn't worked that out, had I? No, sorry. Not quite for the knockout punch yet. That's the last bit of the puzzle. BA times BC is that, apparently, isn't it? Yeah, 2 times 3, and there's nothing there, and minus 2, yes. So that looks like, what's that? 6 minus 2 looks like 4, isn't it? Yes. Excellent. Excellento. Now, here comes the knockout punch now. Let's go for it. So cos theta equals, using our formula from the previous page, is all that stuff, which we've worked out the top, and we've worked out the bottom, haven't we? We've worked out the top's 4, the bottom looks like 3 root 13 to me, so let's go for it. Good, now we just get our trusty calculator out, and we work out the angle whose cos is that thing, and it works out to be 68 degrees to the nearest degree. 68 degrees to the nearest degree. Good? Yeah, and if it came out to be a negative answer, then you just get an angle in quadrant 2 between 90 and 180. But, you know, it's as easy as that. So how do you like that, guys? Now, look, the booby trap in that question is the angle ABC, which means you've got to have the presence of mind to work out vector B to A and vector B to see, and don't go getting trapped into the idea that you use position vectors OA or OB or OC, because they've got nothing to do with it. You've got to, and if you draw a diagram, like I keep telling you to, as nicely as possible, you will see what you have to do. All right, I'll stop raving on. We're nearly finished now, I think, anyway. Just a little bit of a warm down here. A warm down, just to get us finished this very, very interesting little segment of dot or scalar product. What have we got to do here? We've got to simplify A and then expand B. Okay, that's just using our rules. Come on, here comes A today. Hooray. There it is. Good, come on, you do it with me. So it's going to be A dot B minus A dot C, isn't it? Minus B dot A minus B dot C. Now, something's going to cancel, isn't it? Yes, the A dot B with the B dot A, because they're the same thing, aren't they? Remember? Yeah, I've just written them around the other way, and yeah, to make it a bit easier to see. B dot A as A dot B, and move it over a bit to the left. Now we're going to do the cancelling. Goodbye, Mr. A dot B. See you later. So we're left with minus A dot C minus B dot C. That's the answer. Nice and easy. Good show. Now, number B for you and me. Right, so let's do that together. Doesn't that look like a difference of two squares to you? In fact, it is. It is, even though it's vectors. Come on, let's go. That's the statement of the question. Now, that'll be, come on together, A dot A minus A dot B plus B dot A minus B dot B, isn't it? Yes, now, okay, so look, I can see these beasties are going to cancel, can't you? That's the same as that, so they're going to cancel out. Goodbye. So we've got, now, look, this is really interesting. See how this is A dot A? That's actually magnitude of A times cos theta, and of course cos theta is 1 because theta is 0, and cos of 0 is 1. So that's just going to be magnitude of A all squared. And that's going to be magnitude of B all squared. So I told you it was a difference of two squares, didn't I? Yes, it's wonderful. And it's not a vector at all, it's just a number. It's just a number. As was this one here, was just a number. So that's the difference of two squares. It's pretty marvellous, isn't it? I think that's the end. Ah, yes, and you're a star, and huzzah, you'll go far. And hurrah. And I think that's it. So I hope you enjoyed our little foray into the dot or scalar product, and there's more in store next time with vector resolutes, which is also very exciting. Okay, see you.